recording. And we're going to look at lesson 8.1 today, and I guess I should go show you the cover, in this chapter 7 and 8 booklet that we put together. And assuming that you can do all this algebra with exponents, and assuming that you understood kind of the gist of what a log is that you got from this investigation warm-up, today we kind of expand on that idea, and we're going to start by, you know what, actually I'm going to start, you don't have to write this down or anything, I'm just going to start by kind of pointing something out to you that hopefully will make lots of sense. If you think back to the first time you saw this symbol, the divide symbol, you probably saw it like this, something like that, right? And you were taught to think of it as how many of this number does it take to go into that number? Or in other words, if you counted by this number, how long would it take you to hit that number? And of course, 3, 6, there, it took me 2. And that's the way you were taught to think about divide. We usually don't make people think about divide, the theoretical way that divide actually exists, until they get old enough to kind of think that if you understand that multiplying is just really skip counting, well, then dividing is really skip subtracting. But the answer isn't 0, right? It's not like, okay, well, 6 divided by 3 is 0 because 3 goes into 6. No, it isn't. The answer is, how many times does 3 go into 6? 2 of them. So we answer it 2. And the reason I bring this up is because it isn't long after you learn how to write divide this way that you think of it this way as well, right? These two questions say the exact same thing, but they're written very different looking. And then you even learn that there's a third way you can write it, right? All three of these things are exactly the same proposition. How many 2's go into 6? If I skip counted by adding 2's, or actually I just realized I switched from a 3 to a 2. That wasn't very smart. Let's do that better. There we go. That's better. Thank you. Sorry. If I was skip counting by 3's, how many would it take me to get to 6? All three of those different notations say the same basic problem. If I added together 3's, how many would I need to add together to get to a 6? Or conversely, if I took 3's away from 6, how many times could I do that before I hit 0? And the answer to all of them is 2, right? Okay, that logically speaking is kind of the way we're going to think about a logarithm. A logarithm is, instead of skip adding or skip subtracting, it's skip multiplying. You already know, and you're already very familiar with exponential functions, right? Y is equal to some b to some power of x. And back in unit R6, back in, well, I guess it was unit 2, when we did outcome R6, we learned a little bit about inverses. Inverses are where you switch the x and y values. Let's refresh your memory on how inverses work. There we go. Okay, there's y equals x. Its inverse, x equals y, is the same darn line. Obviously, if you switch x and y in those two functions, nothing very exciting happens. But what if I had y equals x plus 1? Okay, so now it's that green line there. And then what if you switched x and y? So instead of y equals x plus 1, it's x equals y plus 1. Whoops, that didn't work the way I wanted it to. Hold on. Undo that, undo that, undo that. There we go. I'll just do it here. Plus 1. There we go. So now those two things are inverses of each other. But what we learned is there is kind of a shortcut way graphically to tell if two things are inverses. If I were to, again, kind of just graph the line y equals x, notice that, and I'll actually make it a dotted line. How about that? Let's make it a dotted line. There, dotted line. There. Notice that that line acts as a mirror image line. Basically, a function, y equals x plus 1, is inversed by reflecting it in the line y equals x. So we learned that way back in the R6 outcome back in Unit 2. And we, of course, apply it to more than just linear situations. Here's y equals x squared, a good old parabola. So imagine now what will x equal y squared look like if we switched x and y. Well, this becomes the mirror, so this point stays the same, this point stays the same, and now it's a parabola going that way. Let's do a more complicated parabola. Here's a parabola where I take x squared and then I move it 3 to the right, 1 down, and I double the x values, or the y values, making it skinnier. So there it is. Try to imagine what the inverse of that is. So this line here acts as a mirror. So that point goes over to about there. This point stays the same. This point stays the same. All right, let's take a look. Let's switch x and y. There you go. Is that what you imagined? Okay, now let's imagine an exponential function. So we did look at graphs of exponentials. It goes through 1, 0, and it, of course, gets infinitely close to y equals 0, but it can't reach it because no matter how many times you multiply 2 by itself fractionally, you still won't get 0, nor will you ever get a negative, so it doesn't exist down there. And of course, it goes up rather sharply because, 2 to the power of 1 is 2, 2 to the power of 2 is 4, and by the time you hit 2 to the power of 3, you're way up there at 8. By the time you're at 4, you're past the screen there at 16. But what if I did the inverse of it? Well, one of the great things about math is that the rules don't change just because I decided to make a different looking function or equation. An inverse happens on a graph when I reflect in the line y equals x. So if I reflect in the line y equals x, I'm down there, which is kind of an interesting looking graph. And we're going to show you today that there's another way that we can write this. Just like I could write the divide symbol, or I could write that little weird bracket and put the answer on top, or I could write divides like they're fractions. I can write the equation x equals 2 to the y as y is equal to the log to the base 2 of x. So these two things say exactly the same thing, and that's what we're going to show you in the notes. These two things here, if you take a function that is exponential, so that the variable is the exponent, and then you make it its inverse, so you switch x and y, now the y value is the exponent, and you can write that in what we call logarithm form, where the base becomes this little b here, y is the answer. Remember, in the original equation, it was the answer, and when we did the inverse, it was the exponent. And we call the x the argument of the log. Please notice that this is not log to the base b times x, right? You do know, don't write this down if you don't want to, you do know that the sine of theta is not sine times a theta. I see that all the time. People decide they can divide both sides of the equation by sine. Sine's not a number, right? It's an operation, and the same is true of logarithm. Written another way, we can say that log to the base b of some number a is equal to c. Now, there are some rules to logarithms. A has to be greater than or equal to 0. You can't take the argument of a log cannot be negative, nor can it be 0. And b has to be greater than or equal to 0 because the base has to be positive for a logarithm to work. And it has to be positive, and b can't be 1. You can think about why that is, if you really want to. Think about it. 1 to the power of 0 is always just 1. 1 to the power of any number is always just 1. So if I was using 1 as a base, I would not have a very interesting log. The y and the x would also have to be 1, and that would be basically it. I'm going to rewrite the way I think about this. I'm going to put this into words. They don't give me a whole lot of room here, so I'll write small. I'll make it big and I'll write small. This is the way I think of this statement. I think if I want to multiply b's, because b's the base, together, it would take y of them to reach x. So I'll give you a sec to copy that down. That's the way I think about a logarithm equation or a logarithm function, like the one I'm looking at. I'm multiplying together b's, and I will reach the number x in y multiplies. So on the little activity we did yesterday, or I guess it was the day before yesterday now, we had, for example, we found out that the log with a base of 10, because that's the one our calculator has, when you press the button that's the calculator and it says log, you're using a base of 10, of 100 is 2. Right? That's what we did. Here, let's make sure we're right about that. Open up a calculator. And if we erase whatever we got on there, clear, we'll say log, and it just doesn't bother saying base 10. We know it's there. Of 100 is 2. What did the calculator just tell me? The calculator just told me that if I'm multiplying 10s together, it takes 2 of them to get to 100. You might look at that and think, wow, what a complicated thing to show symbolically. But you know, again, just kind of an aside here, don't write this down. Think about how complicated that is to explain in words. What does that symbol tell you? It tells you what number times itself makes this 16. Right? It kind of is a big instruction. It's, what number times itself makes 16. That's what this symbol is saying. This symbol is saying if I'm multiplying together b's, I get x if I do y of them. So, notice the base of a logarithm cannot be negative. The argument a of a logarithm is always positive. And let's start now translating exponential into logarithmic. So the base here is 4. If I multiply 4's together and I do n of them, I get m. So the log to the base of 4 of the number m equals n. Notice this statement says the same thing that one does. It just looks different. Right? This is saying I can make the number m if I take n 4's and times them all together. That's what this statement says too. It says if I take the number 4 and I keep multiplying them together, I will get this argument. I will get the m in n steps. All right, let's do one without so many variables. Log to the base 2 of 8 is equal to 3. 2 is the base. 3 is the exponent. 8 is the argument. And again, I say that in my head as, if I'm timesing 2's together, I'll get 8 in 3 steps. Or 2 times itself 3 times is 8. Okay, hopefully, boy, this is really one lesson where I wish I wasn't doing this remote teaching. I'd like to see the looks on your faces, because usually this is where I look out into a sea of 30 students and there's a small number of them just sort of nodding along going, yeah, okay, reasonable, and then there's a whole bunch of people with a very confused look on their face. Because again, we're kind of, it's a paradigm shift. I'm sure the first time you tried to think about dividing using this symbol, it's like, what are you talking about? This is what divide is. Get out of here with that. So you have to kind of think with new symbols happening. All right, now we're going to actually do some evaluating. The log to the base 2 of 16. Let's switch that to something we're more familiar with. Let's switch that to an exponential equation. So 2 is my base, x is the exponent, and 16 is the answer, aka the argument. And okay, how many 2's do you times together to make 16? And the answer is 4. Now, given a little bit of practice, you probably didn't even need to switch this to that, because again, if you read this the way I read it, I'm timesing 2's together and I get 16. Oh, I would need 4 of them. Now, That's going to get harder to do as these get more complicated, right? All right, I'm timesing 2's together, and I'm going to get a quarter. Wait a minute, how's that going to work? Well, now I think for sure we're going to go to an exponential form. The base here is 2. The 1/4 is the answer, and I guess I should maybe say equals x. X is the exponent. 2 to what power is equal to a quarter? Oh, now it sort of makes some sense, because now we can have x be a negative number, right? So x is -2. All right, let's try C. Log to the base 3 of -27, and again I'll say is equal to x. So let's rewrite that in exponential form, because look what it's asking you. It's saying 3 times 3's together until you get to -27. And at this point you might be going, wait a minute. No matter how many times I times 3 by itself, it's a positive number. It's never going to make a negative. And you're right. It did say that the argument, if you look back in your notes of a page, a part of a page there, it said that the argument can't be negative. So there is no solution here. And you can really see that if you put it into exponential form. Because remember, that's the base, that's the exponent, and that's just plain goofy. Right? You could times 3 by itself as many times or as few times as you like. It'll never turn into a negative. So that one's messing with you. They'll do that sometimes. All right, now let's do some equation solving. Those were just evaluations. Now let's do some algebra. So let's trade this for an exponential equation. X is my base, 1/2 is my exponent, and 5 is my argument. What can I do for this thing? Well, I can square both sides. Remember, I'll say recall, x to the 1/2 is the same thing as saying square root of x, right? All right, now this is where we have to kind of say, oh yeah, when they don't bother putting a base number down there, that means we know the base is equal to 10, right? It's kind of like in algebra when I just write, x plus 3. I know that means 1x. And I don't bother writing the exponent 1. I just assume they're there. In logarithms, we assume 10 to be the base when they don't give us a base number. And that's the way our calculator works too. So log to the base 10 of x is -3. So in other words, 10 to the power of -3 is some number x. And I like the fraction answer on that, so I'll just say 1/1000. If you like decimals better, you could say 0.001, right? Tenths, hundredths, thousandths. Note, and we just talked about this, if the base is not indicated, that means it is a base of 10. All right, let's do some tougher things. Log to the base 16 of x is equal to 3/4. So that means that 16 to the power of 3/4 is equal to some number x. And I think you should be able to do that without a calculator. You can think of this as 16 to the 1/4 cubed equals x, right? Because power of a power means that you times them together, and 3 times 1/4 is 3/4. I happen to know what 16 to the 1/4 is. Let me write it this way if you need me to. Right? What number times itself, given 4 of them, makes 16? Aha. Now there might be people who go, wait a minute, Mr. K, I would have thought of this as 16 cubed to the 1/4. And you know what? You're right. It doesn't matter what order you multiply two things in. 1/4 times 3 is 3/4. 3 times 1/4 is 3/4. But do you happen to know off the top of your head what 16 cubed is? Me neither. So, and then once I got that great big number, quick, what's the 4th root of it? I don't know. But I looked at this and went, oh, I know the 4th root of 16. So there you go. Okay, so there you go. That's how I do that one. This works too, but what is it? What is 16 cubed? Okay, don't tell me. 16 cubed is 2 to the 12. Is it 4096? I'm going to just check on my calculator. 16 to the power of 3. Is it 4096? It is. So this is the fourth root of 4096. Oh yeah, right away I know. Oh yeah, 8 times 8 times 8 times 8, that's definitely 4096. Yeah, right. This one I can do with a calculator. That one I had to cheat and use a calculator. So that's why I picked that way. All right. Ooh, isn't D interesting looking? Okay, so let's see. What are we going to do with D? Well, here's what we're going to do with D. 2 is my base. X is my exponent. And this is my argument. And I can do this part in my head. Remember what this part's saying? Let me write it in words again. 3 to some power is 81. Or in words, how many 3's times? How about I'll say multiplied like a grown-up? How many 3's multiply together to make 81, right? And you know that number. You know that number is 4. So 2 to the power of x is 4. And I think I can just figure that out. X is 2. There we go. Stop me if you have any questions. All right. Now, estimating. Everybody's favorites. If you don't have a calculator, how do you figure out what log to the base 2 of 30 is? Well, first thing I'm going to do is I'm going to make it an equation. Say that that equals some number x. Then I'm going to go to an exponential equation. I'm going to say, all right, well, that means that 2 to some exponent is 30. And here's what I know. I know 2 to the power of 4 is 16. And I know 2 to the power of 5 is 32. There is going to be some number x that if you times 2 by itself that many times, you'll get the number 30. But obviously that number is not going to be whole. It's going to be a number somewhere between 4 and 5. So I'm also thinking it's much, much closer to the 5 because 30 is way closer to 32 than 16 is. And I know that exponential scales and exponential graphs, of course, curve upward, right? They curve upward when you draw them. So I know that as we increase, we kind of rapidly increase by more. So even if this number here had been exactly halfway between 16 and 32, I probably wouldn't have guessed 4.5. I'd have guessed something closer to the 5. And in this case, I think it's going to be very close to the 5. So I'm going to guess, my estimate, approximate equal, I think it's going to be around 4.9. Let's check and see how close that is. Now, let's move you over a bit. So let's see. Does 2 to the power of 4.9 make 30? Pretty close. It certainly rounds to 30. What if I said 2 to the power of 4.91? Oh, we're too high. So it's going to be 4.90 something. How about 2 to the power of 4.905? Split it in the middle. Oh, we're a little smaller again, but we're closer. This is off by 400, so that's off by 600ths. You get the idea. I could keep going and find another decimal, then another decimal, then another decimal. Would I ever stop finding decimals? No, I'm dealing with irrational numbers. Now, you might be thinking, isn't there just a way I could type in my calculator what log to the base 2 of 30 is? Believe it or not, even on this big fancy thing, the answer is no. I have exactly 2 log buttons on this calculator. I have a log button that gives me a base of 10, that guy. So if I wanted to know what's the log of 1,000? In other words, how many 10s do you times together to get to 1,000? It better say 3. Yay. The other logarithm button you get is ln, which stands for natural log, and that has a base of e. E is a very fun number that we're going to meet in a later lesson, but we'll leave it for today. If you have a fancier calculator than this, you can have a calculator that will have a log and then a space button and then it's either A or X or something, and you get to fill in. You can ask the calculator what log to the base 2 of 30 is. I actually don't have one of those calculators handy at the moment. Hang on, get that out of there. Oop, yeah, cut. There. If you have, this is a TI-83. If you have a TI-84, it has that. I used to have one of these TI-84s, but I think it was some sort of copyright violation, so TI made it go away. All right, let's try another one of these where we're just going to use our widths and our... This one we actually can check on our calculator because it's log to the base 10. So make that x, and 10 to some x is 20. And okay, let's see. Well, 10 to the 1 is, of course, 10. And 10 to the 2 is, of course, 100. So just using those two benchmarks, I know it's going to be 1 point something, and it'll be very much closer to the 1 than the 2. So I'm going to guess maybe, I don't know, 1.3. That's my guess. Let's double check. Let's see how close we are. Move that over. Come on, move over. Get out of the way. So let's see. This one I actually can find without guessing and checking. Log of 20. And yep, that was a good guess. I'm off by 1,000th. Ooh, good for me. Okay, there we go. And that's example 5. And that's actually it. You can now do the 8 point... Oh, sorry, there is one more. I'm sorry. Hang on. One more, and then that'll be it. So we'll make that x, and we'll say x... No, we won't. We'll say 5 to the power of x is 120. So what do I know? I know 5 squared is 25. 5 cubed is 125. I'm feeling we're much, much closer here than there. So I'm thinking it's going to be, x is going to be maybe 2 point... Actually, I almost want to say 2.9. Do I want to say 2? Okay, sure. Well, let's guess 2.9. What do you think? 2.9. Let's see. Calculator. View over. Does 5 to the power of 2.9 get me pretty close to 120? Oh, I'm way off. How about 5 to the power of 2.95? Oof. Still kind of, how about 5 to the power of 2.99? Even that's not there. This is too low. Let's see, what else could we have? How about 5 to the power of 2.999? Give me another 9. Come back, rabbit calculator, there we go. Even then, I'm not quite there. So it turns out, this is interesting. It turns out the bigger the numbers that I'm trying to estimate, the more I have to kind of compensate for how sharply exponentials curve up. So that means that this is going to be closer to this 3 than, relatively speaking, I'll get to your question in a sec, relatively speaking, than this was to the 5. Or that this was to the 2. So,
So Kelly,
the best
you're trying to get to the 5 or the 3. You're trying to get to 125. You're already close enough. At 2.98.
Oh, right. I was trying to get... Oh, I'm sorry. I was trying to get to 120. Sorry. Okay, let's see. Where are we? Let me try that again. Thank you. Thank you for letting me know that I was kind of going the wrong way here. Let me start that over. So... 5 to the power of 2.95 was what? 115, so not enough. So 5 to the power of 2.99 was too much, right? Oh, hang on. 5. Oh. Clear. 5 to the power of 2.99. That's better. That's pretty good. That's still too low. So how about... Oh, no, that's too much, right? I'm sorry. See, I forgot again. That's too high now. So 5 to the power of 2.9, how about 6? Now we're below it again. So 5 to the power, how about 5 to the power of 2.98? That's too far. So I'm going to say my final guess is 2.97. There we go. But kind of cheated. I needed my calculator to help me a little. Now, is there a way to get, like, lots of decimals on this? Is there a way to get my calculator, if it doesn't have a fill in your own base for your logarithm button like the fancier calculators do? And the answer is yes. And we'll learn how to do that, not in our next lesson, but in the lesson after that. So that's it. That's all I wanted to go through today were those examples. You are now going to work on the 8.1 exercises, which is right here in the exercise book. And, oh, wait, no, that's not it. There it is. Understanding logarithms. And you're meant to try to do as many of these as possible without a calculator. And notice for number 5, it's estimating like we were just doing for the last one. Okay? So there you go. It's only about 5 questions. You got like half an hour. You could be homework free tonight. Wouldn't that be nice? Okay, I'm going to stop the video.